So now we know a bit about the magnitude of stars, we can look at the power output of stars and what we call their spectral output. That's the range of wavelengths they produce. There's two laws that govern this, called Stefans Law and Wiens Law. So we're going to calculate the luminosity of a star, that's the total power that it produces, and we're going to try to talk about how the wavelengths that it produces are affected by its surface temperature. It's important in all this that when we're talking about temperature, we're talking about the temperature of the surface of the star. We're not talking anything to do with the internal temperature at the core. So Stefan's law tells us about the power output. Here's Stefan's law. It says the power output is a constant. Stefan's constant is down here on the data sheet as well, times area times the temperature. That's importantly, that's the temperature in Kelvin, the absolute temperature, to the fourth power. It might look from this equation as if the really important factor in here would be the temperature, because that's raised to the fourth power. But interestingly, it turns out with stars that the range of their areas is so huge that the area is often more important than the temperature. To show you an example of this, the Sun has a power output of about 3.8 times 10 to the 26 watts. But Betelgeuse, which is only half the temperature of the Sun, so it should only be given out a 64th of the power if it was the same surface area. Its radius is actually over 1,000 times the radius of the Sun, so its surface area is more than 1,000,000 times the area of the Sun. Okay, so consequently, it's more than 10,000 times the power output. Sirius, although it's quite a hot star and has a much bigger radius than the Sun, actually produces less output power than Betelgeuse, so it's 4 times the temperature roughly, which means you might think it would be 256 times the power output, but in fact it's less because of its much smaller surface area. So that's Stefan's law. It's worth noting on this that you might think that we can look at stars and see their area and see their temperature and therefore work out their power output, but in fact for nearly all stars working out the area is impossible by visual observation. So what we're actually doing is working out the power output, and that tells us the area of the star. So this is interesting because it can tell us how big a star is. That'll become quite important quite soon. Okay, so the second one is Wiens Law. Wiens Law tells us about the peak wavelength output of the star. It's derived theoretically in the first place, and this is derived for what are called black bodies. Okay, it might seem ridiculous to think of a star as being a black body, but what you have to understand is that if you take something that's black and heat it up and it gets red hot, that doesn't actually stop it being black. Okay, black just says that it's a perfect emitter and absorber of radiation. Okay, so what we're saying is that if you take something black, you heat it up, it goes red, eventually it goes orange and white, and even blue hot, but it's still a black object because it's giving off exactly the set of wavelengths that you would expect. Okay, Wiens Law says that the peak wavelength, this is important, this is not lambda max, looks like maximum wavelength, but it's not the longest wavelength that it produces. That would be very long indeed. What this means is the wavelength with the maximum intensity. That number times the temperature in kelvins again, is a constant. Okay, here's the constant, Wiens constant. Okay, so what that means is that if the temperature goes up, the peak wavelength goes down. This little animation hopefully will make that clearer for you. Here's the output of a star. It follows this characteristic curve. This star is 3000 Kelvin. Here's its peak. So this number times 3000 would give you Wiens constant. Okay, what happens if we put in another curve? Okay, of a higher temperature. Well, what you notice is that the peak goes to the left. That's a shorter wavelength on this scale here. And also, at every single wavelength, the intensity increases. Okay, as we go hotter and hotter and hotter, the peak gets shorter and shorter and shorter, so this star is starting to peak inside the visible spectrum. If we get even hotter, then we're peaking somewhere around the middle of the visible spectrum. So here's the Sun, somewhere around 5,500 Kelvin. Okay, there. If we get a very hot star, then we start to peak over into the ultraviolet, and you'll notice these stars are giving off more energy at every wavelength. The area under this curve indicates the total power output. Here's our red star, Here's the sun, here's our very hot star. Okay, just bear in mind that these would only be a comparison between stars with equal area, so if the red star was huge, it still might be giving out more power. Okay, so quick summary of those things. Hopefully you've got that. So a black body is not something which is black, it's something which is a perfect emitter and absorber of radiation, so it might be emitting all the colours of the spectrum and look white, but it could still be a black body. As you heat an object up, okay, it will start off being black, it will turn red hot, then it'll go orange, eventually somewhere around 6,000 Kelvin it'll go white hot. Once you go past that, it starts to give out more blue light than the other colours of the spectrum, so it looks blue hot, and eventually it's so much dominated by blue that it can actually be a blue object. Okay, peak wavelengths. Okay, the sun is in the visible. Betelgeuse is in the infrared, so it's going to look red because it's giving off much more of the red end of the spectrum than the shorter wavelengths. Sirius, 11,000 Kelvin, is a pretty hot star. Okay, it's actually got a peak wavelength in the ultraviolet. Okay, so the sun is giving off all the wavelengths, it'll look white. Betelgeuse will look red, and Sirius is a blue-white star. Okay, we can do something else with this just to introduce this idea to us. We can work out the temperature of deep space. Here's the peak wavelength of deep space, 1.06 millimeters. Work out the temperature that corresponds to that wavelength, and we end up with 2.74 Kelvin. So one way of thinking about deep space is it's 2.74 Kelvin, although as we'll see that's maybe not quite the correct way to think about it, because what we're really saying is it's been redshifted down to those wavelengths.